We're gonna jump in here. And I loved Adrian's answer for this. Why didn't we learn about L'Hopital's rule in Unit 2 when we were learning about limits? Nice and loud so everybody can hear.
Oh, because we had to learn about limits first.
But that's not what you said before. We didn't know how to do what? We were finding the limits. We were studying about indeterminate limits. We didn't know how to find the derivative. So L'Hopital's rule, you need to know how to find the derivative. And guess what? We didn't know how to do that until units 3 and 4. So so that's when we were stuck with, and you can look behind Caitlin, she can point to us. That's when we had all those indeterminate forms, and then we had to factor, do the conjugate, the common denominator, and all those things. So that was a big conversation for us. All right, let's talk about number 2. When would you not use L'Hopital's rule? When do you not need it? Yeah. So in order to use L'Hopital's rule, you have to have that indeterminate form. So this conversation here is our indeterminant indeterminate form. So if you don't have an indeterminate form, you don't need to use L'Hopital's rule. Number 1 rule of finding a limit is what? Number 1 rule of finding a limit. Plug it in. Plug it in, right? So if we have our number 1 rule is where you plug it in, and if it works, then guess what? You don't need L'Hopital's rule. If you can plug in the limit and get a limit, you don't need L'Hopital's rule. All right, so here I have you finding the following limits. Trick question, which one's not a limit? Yeah. So guess what? Grace is right. Guess what? This isn't a limit. Exactly. It's not a limit. And Kara asked a great question. She's like, well, then why is it there? I'm going to get to that in a minute. Because if you're asked to find a limit and somebody gives you a question that's not a limit, it's not L'Hopital's rule. Are you with me so far? All right. So somebody give me a summary of how I find the limit. What's my first step that I do? Plug it in. So I'm going to take 2. Find the following limit. So I have 2 plus 2 over 2 squared is 4. 3 times 2 is 6 plus 2. 4 over 10, 12 simplifies to 1/3. Am I using L'Hopital's rule? How come? Because it's not an indeterminate form. So if somebody asks you to find the limit, you have to plug it in first, because the only time you're using L'Hopital's rule is if you get this or this. Did I get that there? Did I get that there? No. All right, let's go on and do this next one. I want the tangent of 0 minus 0 all over 0 cubed. So Caitlin is going to point to where 0 is on our unit circle. And she's going to point above it, and you can see your cosine and sine is 1, 0. So my tangent is my sine over my cosine, right? So in our ordered pair, 1, 0, remember this is our cosine, and this is our sine, and our tangent is our sine over our cosine. So if I put my sine over my cosine, I get 0 over 0 over 0. And guess what? That's an indeterminate form. Now I need L'Hopital's rule. Definitely need more space. What is L'Hopital's rule? We need to wake up Nate. What is L'Hopital's rule? Yeah, so this is what Grace said behind her mask. How long do you think till we're maskless? March 1st?
They already said it. They made it official.
Guess what? For you. Right? That just means I'm not going to talk and you guys have to do all the talking. But I'm so excited to see all your faces again. I really am.
Part of our
I feel like I'm kind of swimming upstream here, fighting a battle. Can I have your attention, please? Trying my hardest to tell you what's on the quiz. Okay. Indeterminate form. So as Grace told us, you take the derivative of the numerator and denominator separately. So the derivative of the tangent of x is secant squared of x. You with me? Right? Secant squared of x. The derivative of x is 1. The derivative of x cubed is 3 times x squared. Uh-oh. When I put 0 in, the secant of 0, secant's friends with who? Cosine. So the cosine of 0 is 1, so 1 over 1 minus 1, uh-oh, still equal to 0. Put 0 in, now what? What do I do? I'm going to take the derivative again. So when I take my derivative again, the derivative of my secant is what? So 2 times my secant of x to the 1 last power. Chain rule. The derivative of secant. Because isn't this the secant of x squared minus 1? Right? And the derivative of secant, check out the back, is secant times tangent. Secant of x times tangent of x. And that 1 goes away, which puts me at 6x to the first power. Uh-oh. So the secant, as x approaches 0, the secant is friends with cosine. So it'd be 2 times the 1 over the cosine, right? So 2 times 1 times the tangent is going to be 0, so that's going to 0 that whole thing out again, right? So I end up with a 0 over 0. What? So I need to find the derivative again. And I have my product rule. Are you ready? So I have my derivative of this product is going to be my first term, 2 times the secant of x.
Can't you like simplify the 2 and 6 and
Yeah, let's go ahead and do that. I think that's a great idea. Because we can call this 2 times secant squared of x times the tangent of x. There's no plus sign, so there's no need to distribute. We like that better, huh? Okay, so my first term is going to be 2 secant squared x times my derivative of my second. Derivative of tangent is secant squared x plus the derivative of my first. I'm going to need another Post-it. Here's my first term times the derivative of my second. Now I need the derivative of my first, which is going to be 4 secant of x times chain rule. Secant of x tangent of x times my second tangent of x. And this is what we were all hoping for, was we finally get the 6 in my denominator. Mental note, next year leave more space. Let's double check that. Here's my first term times the derivative of the second. Derivative of my first term is this comes down for this to the 1 less power times the derivative of what's inside times the second term. I think I got it right. Over 6. So let's talk again about where we're talking about. X has a value of 0, which means its ordered pair is over 1 up 0. So its secant is equal to 1 because its cosine is equal to 1. Its sine is equal to 0, which means its tangent is equal to 0. So anything that's times the tangent, bye-bye. You okay with that being so fast?
Yeah.
Tangent is sine over cosine, right? So do you see all these secants? Hey, this is the good part. Anthony, come here. You're going to like this. See all these secants? They're all 1s, right? So my derivative winds up being 2/6 or which is the limit? Hey, the moral of the story is here. And the reason why I put this on here. Next time, I'm making this a squared, so we have 1 less iteration for next year's kids, right? But make them suffer. But your big idea is this. I sure hope you're listening. Your big idea is this. You can keep taking the derivative until you stop getting an indeterminate form. You don't use L'Hopital's rule if you can find the limit. If you're not given the limit, and we're not going to make you do this one, but just so you're all on the same page, this is the quotient rule. This is not a limit. It's not L'Hopital's rule. The quotient rule is low d high minus high d low squared the bottom, and away we go. So this one is asking you to simplify this. This is asking you for what is the derivative, and that's low d high, which is 12x plus 1 minus high 6x squared plus x d low, which is 1, square the bottom, and away we go. So the quotient rule and L'Hopital's rule, 2 very different things. This is finding the derivative of a quotient. This is applying L'Hopital's rule to each of those numerator and denominator functions separately. And you can keep going until it works out. Sound okay? All right. Post-its away. Given that equation, now we're done with L'Hopital, and this is up to what we talked about last time, 6-2. Mean value theorem, MVT, and down here is IVT. Go back in your notes and ask your group mates, hey, what's the difference between MVT and IVT? Marcus at top, go. Difference between MVT and IVT, who can tell me? MVT and IVT, come on. Come on, come on, who's got it?
When you have like any point two to that values can exist, like when all values are open to process, and then MVT is like you have average rate of change at any point on the, or there will be one point on the instantaneous rate of change of the same shift.
Perfect. Perfect, no, you just did great. Okay, so MVT, your mean value theorem, says if you have a function and you find your average rate of change is basically your slope of a secant line. If it intersects a graph twice, it tells you there is going to be between these two values a time when the slope of the tangent line, when that instantaneous rate of change matches the average. If the average rate of change exists on an interval, there's going to be a time between those two x values where your instantaneous rate of change is the same as that mean value. So we can do that two ways. First of all, we end up figuring out what is the value of the function at each point of my interval. And hey friends, if you haven't figured this out yet, let me be the first to tell you. Put the equation into your y equals. Are you with me? This saves you time and stupid mistakes. How many people have made a stupid computation mistake that has messed up their whole answer on their problem before on a quiz or a test? Pete's like, yes, that's been me. Hey, me too. Which is why, because what ends up happening, my brain starts like giddy-upping ahead, and I'm like, oh wait, and then next thing you know, I can't add 2 and 3, and I get 6, right? So you're going to do this, and in case no one's ever told you or you forgot about this, your graphing button shows you the picture of the graph, okay? But this second table function that shows you your input-output. So if you notice on my keys, you don't always see me doing the work because I go to the table of values and I do this. So that saves me an awful lot of time on something. So when I'm looking for the slope, I'm looking for the change in my output compared to the change in my input. This is my average rate of change, which means 64 minus 4 over 5 minus negative 1 is going to be equal to 60 over 6, which sounds a lot like 10. Units per unit, whatever we're talking about. That is my average rate of change. That is my slope. That is Algebra 1 fun. What we know now because of the mean value theorem, I want to know where is the instantaneous rate of change equal to that. So what I'm going to do is take my function, y is equal to x squared plus 6x plus 9. I'm going to find the derivative, 2x plus 6, and I'm going to see, hey, when is this equal to that? 2x plus 6, 2x is equal to 4, x is equal to 2, right? So my mean value theorem says there is a time when this average rate of change is going to be the same as the instantaneous rate of change. So I'm like, okay, so I'm going to take the derivative. Hey, you're going to lose points if I don't see the fact that this is the derivative. So you know how I end up writing DER here to let everybody know that this is my derivative? Your goal in doing work, and I'm saying this after grading your tests this weekend, your goal is to communicate your hard work to me as clearly as you can. You want me to know when you're finding the derivative because I want to be able to give you partial credit for knowing that you have to take the derivative. If I can't read your work, I can't grade it. You have to know that. You guys are seniors moving out into the real world in a minute. If you can't communicate your work so that somebody can read it, what's the point of doing it? All right. So here I went ahead and I found the derivative. I set it equal to my average rate of change. And I'm telling you, at a value of x is equal to 2, at a value of x is equal to 2, that rate of change is going to match. So this is the answer here. X is equal to 2. As Kira did a great job explaining, the intermediate value theorem means that on any given interval, so we're talking about from 14 to 18 seconds, could you justify that Chloe Kim was 29 feet in the air? Yeah, because it's lower than that relative max, right? And so it exists. She can't go from 31 to 0 and back up to 27 without at some point in time being at 29. So the IVT is looking at those minimum and maximum values. All right, quickly, turn over, take a look at your homework, ask me questions on any ones that you don't understand, and I'll be glad to answer your questions. Questions that I want to take the time to answer. Your mean value theorem, we need the function to be continuous across the interval and differentiable, meaning, and the only difference between continuous and differentiable is whether or not you do a sharp point, right? So the only time that it's yes continuous and not differentiable is if you have that sharp point, like this guy here. Okay, so you can use the mean value theorem as long as it's continuous on the closed interval and differentiable on the open interval. So pay attention to the brackets there. Any questions on this first page? Things you want to talk about on that first page? Yeah.
Do you care if it's a decimal or a fraction?
So if it's a decimal that terminates, I'm fine with it. You can never go wrong with a fraction. All right, so some questions on following up here, and I'll try to zoom in a little bit more. So I'm really happy that Kaylee asked me this question. She's like, if I don't pull this 1/4 out, I don't get the same answer. And it took us a little bit of a minute to figure out. She was doing L'Hopital. And that's the hardest thing. When you know how to do the quotient rule, and then someone teaches you L'Hopital, suddenly you don't do the quotient rule anymore. So if you don't pull your 1/4 out when you're doing your derivative, then you have to make sure that you're doing low D high minus high D low, the square of the bottom, and away we go. Because you can't use L'Hopital, because she's like, I took the derivative of 4 and I got 0. Isn't that the derivative constant? Yeah, it is. But this is not a limit. So no L'Hopital. You have to use the quotient rule. So the conversation with the intermediate value theorem goes like this. It is more of a theoretical conversation. If the value of the function at the beginning of the interval is positive, and the value of the function at the end of the interval is negative, it crosses 0 somewhere. It's not asking me to find the 0. I can if they want me to, but they didn't ask me that. Are you with me, fellas? They didn't ask me to find the 0. They just said, is there one? And the intermediate value theorem says, yes, there absolutely is one. Okay? Any other things I can answer for you? Yeah.
Isn't the last question a no instead of yes?
Okay. Oh, yes, because. Just because. Let me think. Maybe I stopped working on it. in the interval of 10 to 15, is there a time when my velocity is equal to negative 20? Oh, that would be a no. Absolutely, up until you told me that. I know. So you really gotta watch your negatives because it's not going to go as low as negative 20 here. It'll hit positive 20, but it's not gonna go as low as negative 20. Sound okay? Yeah. Say that again? Do I mind going over 5? Okay. Number 5 says, my instructions are use the mean value theorem to find where the instantaneous rate of change is equal to. And I'll try to zoom in a little bit more so you can see it because it's on this half sheet. Okay. This is my function. So I need to know the input-output at the beginning and end of my interval. So I plug 0 in, square root of 0 is 0. I plug 3 in, the square root of 3 times 3 is 9. Square is, okay. So are you okay with those as my x and y's? Okay, so now I'm finding my slope. So output minus output over input minus input. I was consistent in how I did it, so I'm confident my slope is 1. So now what I'm going to do is I'm going to take my function. I'm going to take the derivative of my function. And I did 1/2 times this. And it's times the middle to the 1 less power. And whoever said, are you going to change all that one? That's where that 3 comes from. Okay? So then when I have my derivative, now what I'm going to do is I'm going to set my derivative equal to my slope. And then picture this over 1, and I did cross products. Or just multiplied each side of the equation by what's in the denominator. And that's how I found it. My Lord. All right. Do me a favor and clear your desk. We're going to talk about just more parts of graphs because what we're going to start looking at is what is the behavior? What's happening with the graphs across each of these intervals? So we're going to talk about the extreme value theorem. We're going to talk about global and local extrema and critical points. To find the increasing and decreasing intervals of functions. So this lesson is really part 1 of 2, but we're just going to start talking about a lot of this stuff. And a lot of it is a review of your graphing conversations you had in Algebra 2 and pre-calc, but here we go. All right, the extreme value theorem. So far we've had the mean value theorem and the intermediate value theorem. Now we're going to talk about the extreme value theorem. And that basically says if a function is continuous over an interval, then it has at least 1 minimum value and 1 maximum value on that interval. So again, that conversation about it being continuous on whatever interval we're talking about. So depending on your teacher, the absolute and global minimums or maximums, the word global and absolute, they're synonyms. So I've heard them both. Do you remember what your Algebra 2 teacher used? Global or absolute? Absolute? Okay. So, but basically what we're talking about is no point on the graph is higher or lower than that graph. So here, we're going to have our absolute maximum. Because that graph, there's no point on the graph that is higher or lower than it. And then here, we're going to have our absolute minimum. Because no point on the graph is lower than that one. So typically, if you use the term absolute, then you're going to talk about relative minimums and maximums. And the relative minimums and maximums are where you look to the left and the right. And if the points on either side are either both lower than that, then that's a local or a relative maximum. If there's 2 points that are a little higher than that, then that is a relative minimum. So when we look at each of these, this point here, if you look and you trace it back to the x-axis and you create an interval on either side of it, if you look at the 2 points on either side, are they both above that xy ordered pair, that coordinate? So if I look to the left, is this higher? If I look to the right, is that higher? Which makes this one a local or a relative minimum. Because either of these 2 points on either side of it are higher than it. It's not my absolute minimum because it's not my lowest point on the graph. We can also talk about this point here, trace it back. And when we talk about this one, because on either side of this interval, there are points that are higher than it, we can also call this one a local minimum or a relative minimum. There's a bit of drama in the mathematics community right now, and that is what to do with this one. Nobody argues that this is an absolute minimum as the lowest point on the graph, but whether or not we can call this a relative maximum is up for debate in the mathematics community. If you talk to 10 teachers, 5 would say one that yes, you can call it a relative max, and the other 5 would say no, it's an end point, and there's nothing on the graph that is on the other side of it. So in this class, we're going to leave it be. So we're not going to bother labeling it something that we're not so sure that it is. Sound okay? All right. So what we're going to start talking about these critical points, and our critical points are going to be important things for us to figure out how the graph is changing. And they are points that have the possibility of being either a minimum, a maximum, relative, local, global, whatever. And how to find the critical points is we look for either an area where my derivative is equal to 0, or we look for an area where my derivative does not exist. So take a look at this squiggly graph right here, and with your group, tell me where you think you'd have a derivative equal to 0 or does not exist. And your mark is set talk. All right, so each of my times that my tangent line is horizontal, that's going to be a point where my derivative is going to be equal to 0. And notice on my one sharp point is where the derivative does not exist. That will be a critical point that we talk about when we're talking about what's happening to each of these graphs. So what I can do then is use our derivatives and our functions to figure out where either my function does not exist or where my derivative is equal to 0. So we're going to go ahead and if I'm looking for f prime of x, it's going to be 3 times 1/3 x squared minus 9. So 3 and 1/3 are going to cancel out. My derivative can factor into x plus 3 and x minus 3. So if I want to know when they equal 0, I'll set them each equal to 0. And I'll say that therefore when x is equal to -3 or 3 are critical points on the graph. And notice we're talking about where things have the possibility of being an extrema. So we're going to say that that's where my derivative is equal to 0. That's where the slope of my tangent line is equal to 0. but without looking at the graph specifically, we cannot guarantee, but those are going to be critical points that we check out. All right. In the interest of time, we're going to skip this one and come back to it at a later date. So let's flip over. And we're talking about the idea of increasing and decreasing intervals. And this is where we're looking at what the graph is doing. And what we're going to do first is we're going to find our critical points. So our critical points, remember, are where we either have slope of the tangent line is equal to 0, or we're going to have a place where you cannot differentiate that function. So what we're going to do is we're going to look on either side of each of these points. So notice I'm going to put a value of 3 in for x, but I'm going to skip a space before it. I'm going to skip another space and put a value of 5 in for x, and I'm going to skip a space, and then I'm going to put a value of 6 in for x and skip a space. Because what I'm going to do is I'm going to look at what the function is doing on either side of each of those critical points. Because here I have my zeros or my derivative not existing. Number 0 is neither positive nor negative. It doesn't have a sign. When the slope of a function is positive, the function is increasing. When the slope of the function is negative, then the function is decreasing. So I can look on either side of each of these critical points, and I can look and say, okay, here, the slope of my tangent line is positive from whatever this value is. So we'll do negative infinity because that's all we know, up to 3. We know that it's positive. When we're talking about between 3 and 5, not including 3 or 5, the slope of my tangent line is definitely negative. From 5 to 6, the slope of my tangent line is positive. And as far as we know, from 6 to positive infinity, the slope of my tangent line is negative. So we can look at those critical points as landmarks in between and see what behavior is happening to our function. All right. So now what I'm going to do here is I'm going to take my function and I'm going to find my critical points, and then I'm going to, in between those x values, figure out if my derivative is positive or negative. I'm going to use a chart to keep track of my information to see what is happening to my function as it changes. So when I find my critical points, my first thing I'm going to do is I'm going to take the derivative. I'm going to set that derivative equal to 0. And then solve for x. So at x equals negative 2 is where I know I have a critical point. So what I care about is the function leading up to 2 and coming after negative 2. So what I have to do now is look at the derivative of my function, and I'm going to choose a point on this side of negative 2. Call one out. Negative what? Okay. -3. So what is the derivative when my function has a value of -3? Which means -2 times -3 minus 4, which is equal to +6 minus 4, which is equal to 2. So what is the sign of my derivative on this side of my critical point? Let's go ahead and find the derivative of a value on the other side of -2. 5. All right. -2 times +5 minus 4. -10 minus 4. -14. What is my sign of my derivative? Yeah. So because I know that leading up to my critical point it's negative, here's where I hit 0, and here's where it comes down. By choosing test points, I can use some math and figure that out. Yeah.
Couldn't we just know from doing the first one, if that one's positive, that the other one's negative, because it says that the function is increasing and decreasing?
Yeah. So we start with an easy quadratic that we're all familiar with, so that when we get these answers, it makes sense to us. Because it's just a quadratic. So if we had a function that was less predictable, like this fun thing, we would still follow that process.
Okay.
But yeah,
If you have
absolutely.
a problem like that on the test where it says something like that, can you just infer and put a negative?
No, because what we want to see is you doing test points and validating on either side of the critical points. But we gave you an easy function to start, because everybody knows this is a negative quadratic that's like this. So everybody knows that the tangent line is going to be positive up and negative down. So it's kind of like we give you the easy ones first.
Thank you.
Yeah, no worries. All right. So we have another function here, and justify your answers. We can say this work up here kind of justifies it. So it's like C above. How about that? Do you like that? Okay. So with your group mates, go ahead and check out this next function. Find the critical points and see what you think. On your mark, get set, go.